So each molecule is colliding about 1 billion times a second. Yeah. All right, so we said that, so the speed of nitrogen molecule is about 500 meters per second in this room, the average speed. Now the question is every molecule going at the same speed? Obviously not. I mean, the fact that we said it, the average speed is that, and that tells you that it's, okay? So what this graph tells you is, this is the Maxwell-Boltzmann's distribution. What this is telling you, the number of molecules with various speeds, okay? So you see there are a few molecules that are going very slow, and then a bulk of these molecules are going at that speed, okay? So this is the most probable speed. That's the peak of the distribution. That's the average speed. This is the RMS speed. So you can see that here are 3 sort of average speeds which are close to each other, okay? The RMS speed, root mean square speed, is the fastest, but here's the distribution of speeds. And this will be extremely important. So there are some molecules that are going fast, okay? So we just talked about this a minute ago. You saw that you put a glass of water in this room, and there'll be a net escape of water molecules from that glass. And the molecules that are escaping are the fastest molecules. Okay? All right, so this is the probability distribution. Again, it's e to the power, so this is how the graph looks like. Yeah. mv squared by 2k t, okay, and so on, times v squared. Anyway, this is the probability of a gas molecule having that speed. What do you think will happen if I heat the gas in this room? What will happen to this distribution? Yep.
It will distribute evenly?
No. Okay, when you heat the gas molecule, they'll start moving faster. They'll be more. So this distribution will move to the right like that. Every gas molecule is speeding up, so the distribution will move to the right. Okay. All right. So here is the distribution at 300 degree Kelvin, and here is the distribution at 900 degree Kelvin. So the distribution. Okay. So this is calculated for nitrogen molecules, 100,000 nitrogen molecules, and here's how the distribution changes. Okay. Water molecules in the tail of a distribution will escape from a pond. That's evaporation. Okay. And again, when will stuff evaporate? When will the liquid evaporate? As long as the relative humidity is less than 100%. Okay. You'll have evaporation. This distribution is extremely important. Inside the sun, at the heart of the sun, okay, what is happening at the heart of the sun? The temperature, by the way, is 15.6 million degree Kelvin. What's happening at the heart of the sun? Fusion. Okay, so what is happening is 4 protons are combining. They form a helium nucleus. Okay. And it turns out that this is a bound state. This guy weighs less than this guy, and the missing mass is converted to energy. Here is the missing mass converted to energy, E equal to mc squared, Einstein's equation. All right, now here's the question. These are protons. They're both positively charged. They're all positively charged. So they repel each other. How come they're forming a bound state? Why aren't they flying apart? So we talked about this before. So meter, and then strong force takes over. So even in the sun, only the fastest protons are able to combine into the fusion reaction. Okay. So that's this distribution of speeds is very important. Okay. So inside the sun, protons in the tail have enough velocity to overcome the repulsive Coulomb force to undergo fusion. Okay, so again, so this distribution is called the Maxwell-Boltzmann distribution. Okay, and you take a sample and you heat it. The distribution goes this way. What happens at infinite temperature? Okay, so all the molecules will be going very fast. Okay. So VRMS is greater than mean speed, greater than most probable speed. All right. So anytime you see a PV diagram, anytime you see this, you'll see this in thermodynamics. What you're dealing with is a gas. And of course, in textbooks, we mostly talk about ideal gases. So PV equal to why is it not filling up? All right, so here's what I'll do. I'm going to hold the volume constant, and I'm going to heat the gas. So right now the temperature is 300 degree Kelvin, the pressure is 30 atmosphere. Okay. I'm going to heat the gas. I'm going to hold the volume constant. Okay. What will happen to the pressure and temperature? What will happen to the pressure? What's happening to the pressure? It's increasing. Okay. That's because the molecules are moving faster. So you guys understood this process? Okay, so what we're going to do is, so represent this in a diagram, in a PV diagram. So now I'm representing it on a diagram like this. Okay, so initially before I did something, the pressure was 30 atmosphere and the volume was 10 liters. Then I added heat to the gas. What happened to the volume? What was happening to the volume? When I just added heat, what was happening to the volume? I held the volume constant. What was happening to the pressure? Increasing. So you see that was the initial state of the gas, and that was the final state of the gas. I represented that process in a very neat diagram. Okay? Let me show you another process. Let's go back there. I'm going to heat the gas again. Okay, so let's I don't want the box exploding. Okay, I'm going to heat the gas. I'm going to hold the pressure constant. What do you think will happen? See, the volume is increasing. and the temperature was increasing as well. But on this diagram, where I'm keeping track of only the pressure and volume, okay, what was happening? So if this was the initial state, the pressure was constant. Okay, so that process was represented by this path. Okay, so PV diagrams are very useful to represent various processes that you do to a gas when your system is a gas. Okay, and these diagrams, you can easily represent various processes, and it'll be useful for analysis. Okay. All right. Do you guys remember what is the graph of this? What is this graph? If you plot that function, that's a hyperbola. The curves look like this. Okay. Okay. And depending on the constant, bigger the constant c, bigger the constant c, the graph will go like that. Okay, they're hyperbolas. All right, so PV equal to nRT, nRT, P equal to nRT over V. So if you hold the temperature constant, you plot P as a function of V, what you get is hyperbolas. And these are called isotherms. Okay. So if you decrease the pressure of a gas, the volume increases along this curve. Okay. If you keep the temperature constant, that's what that is. Yeah, we'll have to replace all these bulbs. See, those bulbs are gone and all that. You want me to turn off that light? Okay. Okay, so now you know what this process is. An isotherm, iso means constant thermal temperature, temperature process. Okay, so that's an isotherm. So this is a lower temperature, that's a higher temperature. Okay, for that gas. Okay, now what we're going to do is we're going to heat the gas from this temperature to that temperature. Here are two different processes. Here's one process, you're going from, let's say, 100 to 101 degrees. You're going along this path. What can you say about this path? Can you tell me anything about that path? Yep. Very good. Pressure is constant. I'm going to heat the gas from here to there, also from 100 to 101 degrees Celsius. What can you tell me about that path? Volume is constant. All right, so here's the deal. So when you heated the gas from 100 to 101 degrees, when the gas got to 101 degrees, what happened? What happened to the kinetic energy of each molecule? I'm sorry? It increased. When you went from here to there, and when you went from here to there along that path, did the increase in kinetic energy per molecule, was it the same? What does temperature measure again? Average kinetic energy per molecule. If the temperature is 101 degree, it doesn't matter how you got there. That tells you the average kinetic energy. Okay? So whether you went along this path or this path to get there, the final temperature is what determines the average kinetic energy per molecule. You guys understanding this? All right, I'm setting you up for something. All right. Do you know what your car does? What does your car do? Your car is a heat engine. It converts heat to work. It converts heat to motion. And here's basically how you do it. Okay. So here's a piston. You put gas and oxygen in there. You light it up. So we'll, instead of lighting it up, we'll think of it as heating it. When you heat it, this piston moves up, and if you sit on the piston, it'll lift you up. So an expanding gas can do work. Okay? An expanding gas can do work. What do you need to do work? I'm sorry? You need energy to do work. You guys understand all those things? All right, let's go back to that graph. All right, when you went from here to there, did the gas expand? The volume was constant, the gas didn't expand. It didn't do any work. So all the heat you added went into speeding up the molecules. When you went from here to there, did the gas expand? Yes. Okay. So now what did you have to do? You had to add heat to speed up the molecules, and then you had to spend some money because the gas did work. So you warm the gas from 100 to 101, and depending on the path you took, the energy requirement was different. Okay? Based on whether you did work or not. Okay? So you see, along this path, you needed more energy to warm up the gas than along this path. Okay? And different paths will have different energy requirements. You're warming up the gas the same amount, okay? But the energy requirement is different. Okay, so when you go along constant pressure paths, the energy requirement is greater than when you go along constant volume paths. Okay? For solids and liquids, the amount of heat needed just depends on the rise in temperature. Gases are different. Okay? So for gases, the amount of heat added in raising the temperature depends on whether you're adding the heat at constant volume or at constant pressure. When you're adding the heat at constant pressure, this heat added at constant pressure is greater than heat added at constant volume. Okay? All right, so we define two specific heats. For solids and liquid, we define just one specific heat. For gases, we define two specific heat. We define specific heat at constant volume and specific heat at constant pressure. Okay? All right, so we talked a lot. I want you to remember the following. PV diagrams are very useful because you can represent complicated process like with lines in the diagram. Okay? You saw that this was a constant pressure process. This was a constant volume process. What was this process? Constant temperature process. What was this process? I don't know. Okay? So, but it's a process. It can be done. Okay? So anyway, you can represent all processes whenever you're working with gases. Okay? These are convenient. Okay? All right, so this is the specific heat at constant volume. This is the specific heat at constant volume. What that tells you is how much heat you add per mole per degree rise in temperature. Okay? All right, so now we'll calculate the CV for a gas. Okay? By the way, so here's a gas. Okay. So here's a noble gas. Helium is a noble gas. It's a monoatomic gas. It has only 3 degrees of freedom. What does that mean? This guy can only have kinetic energy, and it has 3 directions to move in: X, Y, and Z. Okay? So all noble gases, all the last column guys, they all have 3 degrees of freedom. Here's a diatomic molecule. Nitrogen and oxygen are diatomic molecules. And they have how many degrees of freedom? They can also move along 3 directions, 1, 2, 3. In addition, they can spin as well. Okay, so they can spin like that, and they can spin like that. So at these temperatures, those degrees of freedoms are available as well. They can also vibrate, but the gas needs to be at a higher temperature. At these temperatures, those degrees of freedoms are not accessible. It's like saying that Lamborghinis are for sale, but I can't buy them. Okay? So that degree of freedom is not available to me. Okay? Right. I can buy a Honda Civic. Okay? All right, so a gas molecule, this has 5 degrees of freedom. More complex molecules will have higher degrees of freedom. Okay, so this can rotate like that, and depending on temperature, the number of degrees of freedom available. All right, so let's calculate. What we are going to do is we are going to calculate CV for a gas. Okay. So let's say each molecule has F degrees of freedom. So the energy of the gas is N, the number of gas molecules, times F degrees of freedom. And each degree of freedom, how much energy does it contribute? I'm sorry? 1/2 kT. Okay? So there is the total energy of the system, of the gas. Okay? So the energy of the gas is, okay, so this is, okay. This is for 3 degrees of freedom. Let's calculate this. Okay. So I'll calculate, oh, okay, so we'll do the calculation over here. Okay. Okay, so the internal energy of the gas is N times the degrees of freedom times 1/2 kT. Okay, and N is N is number of moles times Avogadro's number times F/2 kT, and Avogadro's number times Boltzmann's constant is the gas constant. Is N times F by 2 times RT. Okay, CV is defined as 1/n delta E by delta T. Okay, CV for a gas, that's the definition. Okay, CV for a gas is 1/n delta E by delta T. 1/n delta E by delta T is this fellow, N times F/2 times. Okay, so this is the specific heat at constant volume, molar specific heat at constant volume. So molar So what this means is if you have 1 mole of a gas and you want to heat it at constant volume, this is how much heat you need to raise its temperature by 1 degree Kelvin. So it tells you if you have 3 degrees of freedom, you need 3/2 R. If you have 5 degrees of freedom, you have 5/2 R. If you have 7 degrees of freedom, you have 7/2 R. All right, so for 3 degrees of freedom, it's 3/2 R. Okay. All right, for a diatomic molecule, okay, so for a diatomic molecule, it has 3 translational degrees of freedom, and these 2 rotational degrees of freedom. That's 5. And if you get to high enough temperature, you get these vibrational degrees of freedom. So that'll give you 7 degrees of freedom. Okay, so CV, the amount of heat needed, will depend on how many degrees of freedom you have. All right, and here's what happens. So Here's the specific heat for a diatomic molecule. So at these low temperatures, a diatomic molecule has only translational degrees of freedom. It has only 3 degrees of freedom. So that's the specific heat at constant volume. So at low temperatures, to heat the gas, you don't need as much heat. At these room temperatures, you have the rotational degrees of freedom in place, so there's 5 degrees of freedom, so you need more heat to heat the gas by 1 degree Celsius. So if you took this gas and cooled it to below 100 degree Kelvin, you don't need as much heat to warm it up. At these temperatures, you need more heat to warm up the gas. And if you took the same gas to the surface of the sun, now the vibrational degrees of freedom are in play as well. You need even more heat to warm up the gas by the same temperature. It's like when you're rich and your spending habits are more, it takes more money to maintain you. Okay, so that's what that means. Okay. So the more degrees of freedom a system has, the harder it is, the more energy is needed to warm it. And why is that? Because when you add heat, you're adding heat to every degree of freedom. And so if there are more degrees of freedom, you need more energy to warm it up. Okay, so that's what this graph is telling you. And it's relevant, so you see this is for hydrogen gas at various temperatures. So to warm hydrogen gas on the surface of the sun, you need more energy than if you warm hydrogen gas at room temperature here. All right, so for hydrogen molecules, separation between lowest vibrational energies is 10 times greater than the average kinetic energy at room temperature. Okay, so these guys, vibrational degrees of freedom don't come into play until the gas is very warm. Okay. All right, that finishes this chapter.